Swayam Prabha. Digital India. Educated India.
We have derived the linear momentum balance, and then we are proceeding towards the Navier-Stokes equation, and we found that the linear momentum balance, the viscous stresses were unknown, and we need to relate it to the velocity gradient. To understand velocity gradient, we have come to solid mechanics, and we are discussing strain, and with reference to this journey to the Navier-Stokes, we were here, okay, having derived the differential form of linear momentum balance. The viscous stresses on the right hand side were unknown. We need to relate it to the velocity gradient. I think now we can have some feel for velocity gradient, having discussed displacement gradient. So, to understand velocity gradient, we came to solid mechanics, and so that you can understand displacement gradient. We introduced normal strain, shear strain, also discussed about rotation, we also discussed about displacement field and displacement gradient. That is where we stand. Now we are going to discuss about this block, which says differential displacement is equal to deformation plus rotation. Let us see what it means. Okay. In terms of outline, this is outline for the our second visit to solid mechanics, titled deformation and strain. We defined the types of deformation, either change in length or change in angle, and their measures are called as strains, namely normal or shear strain. And we found that they are related to the displacement field. So, we discussed displacement field, displacement gradient, 1D, 2D and then 3D. Then we related the strains to the displacement field in terms of displacement gradient. Okay. Now we are going to look at the last two bullets, namely components of displacement, and then as a result of that we will show that the displacement gradient tensor is sum of two other tensors, namely strain tensor and rotation tensor. The motivation for splitting this displacement gradient into strain and rotation we will discuss later towards the end of this lecture. Okay. Now we look at the title, it says total displacement. Okay. Now when I say displacement, it means change in coordinates, that is all it means, nothing more than that. If you have a plate and then you apply a force, it undergoes deformation, there is some change in coordinates. That change in coordinates could be because of several reasons or several components. First, if you just move the plate, it is translation, that is what we have seen. So, that can result in change in coordinate. Okay. Just moves. So, remember you have the same graph sheet. So, your axis is same and your object moves, the plate moves, there is change in coordinate, and that is what is we have seen earlier. We discussed an example where when we changed alpha, this initial state translated to the final state, but there is a change in coordinate, which means it has got displaced. Now what is the second case? If it just rotates, the entire body rotates, once again there is change in coordinate, and that is what we have seen in this case. We took the same displacement field, and this time we kept alpha 0 and gave a non-zero value for beta, and we found that it rotates, but what we are discussing now is by rotation there can be change in coordinate. Okay. We took another case, third case, where there was shear strain, there is change in angle, and once again if you look at this, there is change in coordinate. Okay. And of course we have not discussed normal strain here. This particular example did not have normal strain, but we took another example where we had normal strain, shear strain and rotation as well. Of course, this example does not have translation, but this also we concluded that when there is normal strain, change in the length of the plate, let us say, then there is change in coordinate or displacement. Okay. So, now if you want to put them all together, what are the components of total displacement? We are going to split into the first two are called rigid body motion, that is translation and then rotation. Why is it so? The entire body just moves, something like I moving in this direction and I am just rotating. These two are called rigid body motion. There is no relative displacement between different points in the body, something like what you did in a rigid body mechanics. That is why it is called rigid body motion. And so, rigid body motion could be translation, just moving this way, or it could be rotation, or moving this way and then rotation. Okay. Deformation. So, when we say deformation strictly, it means change in length, namely normal strain, and then change in angle, namely shear strain. Okay. Now, we are slowly trying to distinguish these two very clearly, and that is in fact the objective of this today's lecture also. Total displacement could be because of rigid body motion, deformation. So far we could not have been very formal in using this terminology, but this lecture we have to be very precise and clearly mention what is rigid body motion, what is deformation. We are going to distinguish these two, separate these two, or in other ways dissect the total displacement into its components. What are the components? Rigid body motion and then deformation. Rigid body motion could be because of translation and then rotation, and deformation is because of normal strain and shear strain. What we are going to see is, if we have a displacement, how do you factor that into that due to translation, that due to rotation, and that due to normal strain and that due to shear strain. We are going to separate into we are going to separate deformation part from the rigid body motion part. As I told you, the motivation we will see towards the end of the lecture. Why do we really do this will be discussed later. Okay. Now, how are we going to do this? Okay. The way in which we are going to do this is express displacement gradient tensor in two different ways. We will take displacement gradient, express the displacement gradient tensor in two different ways, and then achieve our objective of splitting the displacement into rigid body motion and deformation. That is how we are going to do. Okay. Now, as a recall to displacement gradient tensor, let us look at the example which we have discussed in the previous lectures. This example was taken to illustrate the displacement gradient tensor for a 3-dimensional case. We said we had a cube, it became a cuboid, and then we noted the initial configurations, the position at the initial state, and then the final positions in terms of A dash, B dash, C dash. Okay. We also noted the displacements in all the directions for these points, and then we wrote the displacement gradient tensor. What we did was, we took particles along one direction, let us say A and B, found out the difference in x displacement, y displacement, z displacement, divided by the distance between them, and then we got values minus 1 0 0. What we did was, we found out these values and then arranged all those values along a column. We said we will justify it later, and then of course similarly for the y direction, z direction, and these are the numerical values. Okay. Now, this particular example shows the displacement gradient tensor for a specific example. Now, what we will do is make this more generalized. This looks as if it is for a particular example. We will make it more generalized, and also you will know why we collected all these values and arranged as a column rather than a row. Okay. So, two things we will do. First, instead of attaching this displacement gradient tensor to a particular example, we will derive more general expression, which expression is going to be same, but in a more general sense, and also we will answer, we will automatically understand why we arranged these values along a column rather than a row. Okay. What it means is, if you look at a column, then it corresponds to difference in displacement x y direction for two particles along x direction, and second column tells same thing for two particles along y direction, third column tells about particles along z direction. Okay. So, if you take one row, it tells about change in x displacement for particles along x direction, y direction, z direction, or tells about change in x displacement along x direction, y direction, z direction. So, why did we arrange like this? Okay. Of course, then we saw this displacement gradient tensor, same slide as what we have seen earlier for one dimensional case, the two dimensional case and the three dimensional case. Okay. So, this just to recall what a displacement gradient tensor is. Now, we will proceed with our objective of deriving the displacement gradient tensor in a more generic way in two different ways, and we will discuss now the first way, can be called as a more mathematical way. Okay. Before going ahead with that, what is shown in this figure are points P and P star, Q and Q star. So, what is shown is, you take a plate, identify point P, identify point Q, and it undergoes change in coordinate. It could be rigid body motion, it could be deformation. Because of that, because of any of these reasons, it could be rigid body motion and it could be deformation, P moves to P star, P moves to P star, and Q moves to Q star. Okay. As I told you, P has got displaced to P star, Q has got displaced to Q star. That displacement could be because of rigid body motion, which is translation and rotation, or because of deformation, which is normal strain and shear strain. Now, our objective is to split rigid body motion or take away rigid body motion from the deformation. First thing what we will take out is translation. What is translation? If you take, let us say, a plate and moves along one direction, every point, let us say if you focus on 2 points, both the points move by the same distance. Let us say the plate moves by 5 centimeter, this, and you focus on these 2 points, both the points move by 5 centimeter. Okay. And that is what is shown here. Okay. R P and R P star are position vectors. What do I mean by position vectors? The vector joining the origin and the point of interest. So, the vector joining origin and point P is R vector P. The vector joining origin and P star is R vector P star, they are position vectors. And what is U? The displacement of particle P denoted by U vector P, and because it is displacement for a point at P, it is denoted as U vector as a function of x, y, z. Okay. So, R P is a position vector for P, R P star position vector for P star, U P is equal to U vector, and that is a displacement of point P, which is at a position x, y, z. Okay. And we will come to Q little later, right now focusing on P. Now, okay, and if you vectorially represent, the vector R P star is equal to R P plus U. Simple vector addition will give you R P star is equal to R P plus U P or U. Of course, U is a displacement field which has 3 components, U x, U y, U z, which we have already discussed, and all 3 can be functions of x, y, and z. Now, what is translation? And our objective is to remove translation and rotation from deformation. Is it very easy to remove translation? And that is what we are going to do first. As I told you, translation, how do you understand translation? You have a plate and the plate moves. What is implication? If you mark any 2 points, they move by the same distance. Okay. How do you represent? Rp star is equal to Rp plus A, where A is a constant vector, Y is a vector. If it is the plate is moving in this direction, it is a scalar, but suppose if it is moves in this direction, same plane but moves in an angle, then it is a vector with two components. But suppose the plate moves in this direction, then it is constant vector but 3-dimensional vector. All these are translations because the entire body moves. I will repeat again, the plate let us say moves along a straight line, these 2 points also have the same displacement, both have the same displacement, and in this case A is a constant vector, just a scalar, A is a scalar. In all the case A is constant, in this case it is a scalar. But suppose the plate gets translated like this, then A is a vector, 2D vector. But now the plate can also move like this, translate like this, in which case A is a 3-dimensional vector. So in a general sense A is a 3-dimensional vector, every point gets displaced by that either scalar or vector. So now how to eliminate or how to remove translation? How to remove translation? Instead of talking displacement of this point separately, if you talk about difference in displacement, they will just cancel out. Let us say you are here P and then another point slightly away, let us say P and then Q, and then if the plate moves by 5 centimeter, P also moves 5 centimeter, Q also moves 5 centimeter, difference in displacement is 0. So to remove translation, what is written here is all points displaced by the same distance in the 3 directions. Okay. And eliminate, how do you eliminate? By taking difference of displacement. So what we will now on work is in terms of difference in displacement. Okay. Reason for working in terms of difference in displacement is it takes care of translation. Translation has been eliminated. If you work in terms of displacement, it includes translation. If there is change in coordinate and if you are working in terms of displacement alone of every coordinate, then it can include translation. We want to avoid that. How to avoid is just by taking the difference in displacement between 2 points on the plate. So next slide onwards, in fact throughout the for further discussion we will work in terms of difference in displacement. Okay. Okay. Remember we are proceeding towards deriving expression for displacement gradient tensor. We are going to do it in 2 different ways and we are discussing the first way now. Before that we said that instead of working in displacement, working in terms of difference in displacement, we have taken care of translation by taking difference in displacement. Okay. And okay, now we will focus on the point Q as well. Now P is at a point x, y, z. I have another point, neighboring point Q, which is at another location x plus dx, y plus dy, z plus dz. Okay. So the x, y, z distance between P and Q are dx, dy, dz. Now the plate undergoes maybe rigid body motion and deformation. P has moved to P star and Q has moved to Q star. Okay. Now the respective displacements are denoted by u vector P, u vector Q. Alternatively, in terms of displacement field, because P is at x, y, z, it is displacement field at x, y, z, and this one the displacement of Q is displacement vector at x plus dx, y plus dy, z plus dz. Okay. Now what is P star? P star is the new position. As we have seen earlier, how do you find out? The old coordinate plus the displacement. Similar for x direction, y direction, z direction. So what is the old coordinate is x, what is the displaced next direction is u x p, similarly y direction, z direction. Now coming to Q star, what is the new coordinate? The old coordinate x plus dx plus the displacement along the x direction for point Q, which is u x q. So, similarly y direction and then z direction. Similarly, you will get the coordinate in the y direction and the z direction. So, we have p q in the initial state, it gets displaced to p star q star, and we have noted the displacement in terms of u at x y z and u at x plus dx, y plus dy and z plus dz. Okay. Now, let us go ahead. So, displacement of p is up is equal to u at x y z. What about displacement of q is uq, but in terms of displacement field it is u at x plus dx, y plus dy, z plus dz. Now, what did we say? We said that we look at difference in displacement, right? Yeah, let us write expression for difference in displacements. As I told you, the reason is it takes care of translation, translation gets eliminated. Okay. Okay. Now, how do you represent difference in displacement? Is d of the u vector. Okay. In our case, the displacement of q minus displacement of p. Displacement of q is given by this u at evaluated at x plus dx, y plus dy, z plus dz, minus the displacement of p is u evaluated x y z. What does this line tell you? The vectorial difference in displacement of q and p. Okay. Tells you the vectorial difference. Right now vectorial, we will go to the component shortly. Right now vectorial difference between the displacements of q and then p. Okay. So, we are looking at 2 points. Of course, here it is shown, remember these points are in a plate which has undergone rigid body motion and deformation. Okay. And remember the points here are shown far away, but they are very near neighboring points. Okay. Now, instead of working in terms of the vectorial difference, which is a little difficult, let us work in terms of component. So, let us now focus on the x component of the previous equation. So, what does this equation tell you? It tells you the difference in x displacement between p and q. Okay. This is the vectorial equation and written a x component of that. So, this tells you the difference in the x displacements of points q and p. Now, we will take this expression, we will take this displacement ux at x plus dx, y plus dy, z plus dz, and we will write in terms of a Taylor series, but Taylor series is familiar to us, and here of course there are multiple variables. So, multiple variable Taylor series. How do you write? You expand about x y z. So, first term is ux x y z, then you have all the derivatives, of course in this case partial derivative. So, dou ux by dou x into dx, dou x by dou y dy, and dou ux by dou z into dz. So, what is that I have done? Taken ux, which is the displacement of point q, it is at x plus dx, y plus dy, z plus dz, expanded about x y z. So, first term is ux x y z, and then all the usually Taylor series is total derivative, but because multiple variables are there, partial derivatives are there, and then we have dx dy dz. Okay. Now, let us substitute this equation here, okay, and what do we have? Ux cancels out and only these derivatives remain. If you substitute in the earlier equation, ux cancels out and these 3 derivatives remain. Okay. What is the other way of looking at it? Ux is a function of x y z and dux is total derivative of ux. You are expressing that in terms of partial derivative. 2 different ways of interpreting this. What I have done is a little more geometrical, physical way of understanding dux. Little more mathematical way is ux is a function of x y z, ux is at x displacement, all the components are functions of x y z. So, ux also a function of x y z. So, expressing total derivative in terms of partial derivative gives you this expression straight away. Okay. Fine. Now, what is the significance of this expression? The left hand side what you have is let us tentatively call as difference. The what you have left hand side is the total difference in x displacement between q and p. The right hand side that has been expressed as 3 different terms. What do they represent? This x displacement is a function of x, y and z. Ux varies with x, y, z. The first partial derivative takes into account variation of ux in x direction. Second partial derivative takes into account variation of ux in the y direction. Third derivative takes into account variation of ux in the z direction. Okay. So, left hand side tells you the total difference in displacement, and that has been apportioned into 3 parts because of the variation of x displacement along x direction, y direction, z direction. So, mathematical statement, total derivative relating partial derivative. Now, let us do this for the other 3 directions as well. Okay. This is same as what I have seen in the earlier slide. Similarly, you can do for the y direction, okay, and similarly for the z direction. What do they tell you? This tells you about the difference in x displacement between p and q. This tells you difference in the y displacement between p and q, and then similarly this tells the z displacement between q and q. The difference in x displacement, difference in y displacement, difference in z displacement. Okay. Now, let us arrange this in a form of a matrix equation. Okay. I will collect all this total difference in right now it is a differential, but I am calling it as difference. I am collecting all the differentials of displacement on the left hand side as a column vector, and then these dx, dy, dz, remember they were the difference in the x coordinate, y coordinate, z coordinate between p and q. They are all collected as a another column vector. Now, if you arrange this as a matrix, then what you get is this 3 by 3 matrix, which you are familiar as the displacement gradient tensor. Now, look at the example which I have seen earlier. We took this example and then found out we took 2 particles along x direction. We found out these 3 derivatives in terms of difference in x, y, z displacement, and then we wrote this as in the form of a column, not in the form of a row. Now, if you compare this of course, later on we wrote this difference in terms of differential. Now, compare this displacement gradient tensor and this tensor, they are both same. That is why we collected all those terms, all those values, and wrote as a column rather than a row entry in this particular matrix or tensor. Okay. Now, what does this tensor tell you? We already discussed that the left hand side we have the displacements, and the displacements are x, y, z directions, and each of them can vary in x, y, z direction, which are here, and hence resulting in 9 components of the displacement gradient tensor. Ux, uy, uz themselves have directions, x displacement, y displacement, z displacement. All of them can, each of them can vary in x, y, z directions, that is what is given here. So, the tensor connecting these two has 2 directions attached to it. Okay. And if you write in this way, one row corresponds to the x displacement along x direction, y direction and z direction. And when we wrote here, we took particles along one direction and considered their x displacement, y displacement, z displacement. So, in the displacement gradient what happens is, along the row you have only x displacement, y displacement, z displacement, but when we consider here the particles, we consider 2 particles along x direction and consider their x displacement, y displacement, z displacement, difference in x and y and z displacement. That is why we wrote them, collected them and wrote as a column rather than a row. So, one row belongs to a displacement in one direction, but when he wrote from here we took difference in displacement along 3 different directions considering particles along one direction. That is why we collected and wrote them as a column rather than a row. Okay. So, of course, that time it was not possible to explain the reason. Now, we have a very good reason to explain why we wrote those elements as a column rather than a row. And also we said that this displacement gradient tensor was looked like for a specific example. It is not the case. We have written a more general, we have derived the displacement gradient tensor in a more generic way, and so what we have derived is a more general form of this displacement gradient tensor. Okay. Same form, but we did not restrict to a particular geometry, we did not restrict to a particular configuration, we have derived in a more general sense. Okay. What we have done now is derived a relationship between the total difference in displacement or differential in displacement. We almost use this word synonymously throughout the lecture. Okay. Differential and difference. So, we have related the differential in displacements to the differential in the directions x, y, z in terms of a displacement gradient tensor. Now, we are going to this more mathematical. We took 2 points, looked at the difference in displacement, etc. We are now going to arrive at the same expression more geometrically, and that is what we are going to do now. Okay.